Hi, this is Mrs. Clark, and welcome to my video about compounding the problem. This is lesson 2.6, and we'll be working through this worksheet. You will be, following along as if I was teaching you in the front of the classroom, pausing to try to do the problems on your own, and then, coming back to check to see if you have the work correct. So use the video as you would follow along in class if I was giving instruction. When it says to pause, pause, try the workout on your own, unpause to check your work, see if you did it correctly before you move on. If you just pause the video and don't really listen to what I'm saying, you're not really going to get a lot out of the video. All right, so we did some work with interest at the boards in groups, and now we're getting a little bit more formal of an understanding of what we were working on. So we'll start here. You probably don't have a ton of money sitting in a savings account yet, but let's say you have $100 and want to do something smart with it. Instead of just letting it sit there, you start thinking about how you could actually grow that money over time. One option is a savings account that uses compound interest. So this is a word I did not use the other day, but when we were working at the boards, I was giving you different versions of savings accounts where sometimes the payout was given at the end of the year. Sometimes you got it twice a year, once in the middle of the year, and then once again at the end of the year. Then we moved into getting paid out 4 times a year. Then we moved into getting paid out 12 times a year, and so on. And so that's what compound interest means. It's interest that is compounded over time. And so that means that um, sometimes it's given annually, which is 1 time a year at the end of the year. And then other times it's given semi-annually, which is 2 times a year, or quarterly, 4 times a year. And that means that the bank pays you interest not just on the money that you put in, but after you get that first payment, you now have more money in your account. So the next payment, the interest is based on that new amount of money in the account. And so over time, that can really add up. So you may remember that compound interest, you've talked about it before if you've had personal finance already, or you may have looked at this a little bit in Algebra 1, but it is an exponential function. You definitely talked about those in Algebra 1. But this is the formula, and that's probably very new to you. So let's talk about the different pieces of this formula and think about how um, they all relate to each other in here. So we're going to practice putting the numbers into the formula, but first we need to know what each piece is. So if we look at this formula, we have A over here. A stands for the amount of money in the account at any time. And so that means after whatever amount of time they say, this is what A is, how much money is in your account. The P on this side stands for the principal or the original amount you invested in the account. So how much money did you put in? How much money started in your account? That's what your P is, your principal. The formula will always have a parentheses and a 1 here, and then it will always add on this fraction, where R at the top stands for the annual interest rate. So remember, annual just means in a year. And that interest rate has to be in decimal form. And then that goes on the top here. On the bottom is N, and N stands for the number of compounding periods each year. So they will tell you that in the problem, whether it's once, twice, 4 times, 12 times, or any other time that they're looking at. And notice your N is in the bottom, the denominator of this fraction, but it's also up here in the exponent. So be aware of that. And up here, it's being multiplied N times T. T stands for the number of years, and that's the number of years after you've put money in the account. It's accruing interest over time, and then after that number of years is when you're going to see how much money is in the account. All right, so one thing that's important to know is that these are being multiplied to each other. And then when we simplify this, we're going to simplify it using PEMDAS. So we'll talk about that when we do the first problem here. All right, so anytime we're reading a word problem, we should be reading it once to get the general idea of what it's saying, and then reading it again and annotating as we read to make sense of some of the information that's given to us. So if your savings account pays a generous 5% per year and is compounded only once each year, how much money would be in the account at the end of 1 year? So I heard a lot of numbers in there, some words in there that I'm not super familiar with. But I'm going to go through again and I'm going to underline or circle things and then try to find where these different variables are in this sentence. So if your savings account pays a generous 5% per year, so this sticks out to me, this number, not just because it's a number, but because I see the word percent or the percent sign, which tells me that that's a rate. So that's going to be our annual interest rate. That's our R, and we have to put that in decimal form. So R is not going to be equal to 5, but it will be equal to 5 out of 100, which is 0.05. So annotating this also shows that you understand what you're reading and how that translates into the math we're doing, which is super important for criterion D. All right, then it says, and is compounded. So there was a new word that we learned today, compounded only once each year. So up here it talks about compounding. N is the number of compounding periods each year. So this says once each year, which means N is going to be 1. So N is whatever number is happening each year. And sometimes it's going to be written in words and sometimes it'll be written in numbers. So you have to look carefully. Don't just go through and only look for numbers like this one. And then it says how much. So that's the beginning of a question. How much money would be in the account at the end of year 1? How much money would be in the account? So the amount of money in the account at any time is A. So since it says how, that means we're looking for that amount. So that means we don't know what A equals. So I'm going to put A equals question mark. So I remember that's what I'm trying to find. And then it says at the end of 1 year. So here's another amount of time in years. So T is going to be the number of years. So T is going to equal 1. So if we look, we have T, we have N, and we have R, and we're looking for A. So we need to figure out what P is. They actually told us P in the story, but it doesn't say it right in this sentence. It says if your savings account. So if you remember up here, we were talking about a savings account, and we said we were going to put $100 in it. So right here, this is our amount that we're putting in it. So that's our P. Normally, it would be written in the same problem down here, but because this is kind of stretched out with the story, it's written up there. So P equals 100. So when we go to fill in our equation now, we have to follow this formula up here, exactly how it's written, and we're just going to put in numbers everywhere we have numbers. If there's no, we don't know the number for the variable, we'll keep the letter. So at the very beginning, it starts with an A, and I don't know A. So I'm just going to start with A. And then I'm going to put an equal sign because it has equals. And then instead of P, I'm going to write 100 because I know P is 100. Then I have a parenthesis, so that comes next. Then there's a 1 plus, so I'm going to do 1 plus. Then I have to put my R. And my R is 0.05. So I'm going to put that on the numerator over N, which is 1. Then I'm going to close my parenthesis. And then these are exponents. So I'm going to write them small and up here. And I'm going to multiply them times each other. So N we know is 1, and T we know is also 1, so it's just going to be 1 times 1. And that looks kind of silly right now, the way it's written, but we're going to keep it like that so that we show that we knew where every number went in the formula, and we're putting it in the proper place. Next thing we're going to do is we're going to just simplify one piece at a time. And to do that, we're going to follow the order of operations, which is PEMDAS. So PEMDAS says that we start with the parentheses, and we simplify everything we can in the parentheses. So what is in the parentheses right now? Well, I have 1 plus 0.05, so I'm divided by 1. So I'm going to put all of that into my calculator, so this whole thing right here. I put all of that into my calculator. We can type that whole thing in just like we see it. I'm going to show you how to do that real quick. All right, so I got my calculator. I'm going to type in 1 plus, and then I'm going to do 0.05. And then to get the fraction, I'm just using the divide sign and then a 1. So it looks like this. And when I hit that, it's going to tell me everything that I highlighted orange is all equal to 1.05. So I'm going to rewrite everything in my equation. But when I get to the orange part, I'm going to put 1.05 instead of all that. So A equals 100 parentheses. I still have to keep the parentheses even though I condensed everything down to one number. 1.05, close my parentheses, and then my exponent is 1 times 1. I have to keep the parentheses because they're attached to this exponent. So until I get rid of that exponent, the parentheses have to stay. All right, so next thing that we're going to do is we're going to do our exponents. So that's this part. That's the start of it, is that part. So P stands for parentheses. We did that. Now exponents, we're doing that next. So A equals, didn't do anything with the 100 yet, but what's 1 times 1? Well, hopefully you know 1 times 1 is 1. So it's really 1.05 to the first power. So the next thing that I need to do is actually do this part here. What is 1.05 to the first power? Let's type this into our calculator and figure out what that number is. So 1.05, use this little button over here, to the first power, hit enter. Well, duh, we knew that. Anything to the first power is itself. So A is equal to 100 times 1.05. Well, I kept the parentheses because I want to remember that this 100 is times the 1.05. So now that I've done my exponents, the next thing I do is any multiplication that there is. So I'm going to do 100 times this number. 100 times 1.05, and that's 105. So A is equal to 105. I do not have to do any division or any addition or subtraction because I've cleaned up the parentheses, I cleaned up the exponent, I did the exponent, then I did my multiplication, and now I just have one answer, so I'm done. The most important step when I'm finished is to take this number that I got for my answer and turn it into a sentence. So I want to turn this question around. How much money would be in the account at the end of 1 year? I will have $105 in my savings account after 1 year. So if I let that $100 sit in my drawer at home for a whole year, I'll still have $100. If I took that $100 and put it in the bank, at the end of the year, I would have made $5 in interest without even doing anything, just not using it and letting it sit there. So the next question is going to have us use the same bank account information, but they want to know how much money would be in your account at the end of 20 years. So instead of the end of 1 year, I'm now going to do 20 years. So instead of T being 1, T is now going to equal 20. But it's the same bank account. So I'm going to have the same initial investment of $100, same principal amount. I'm still looking for how much, right? So that's still going to be A equals. And then my rate is still 0.05. And my N is still 1. The only thing that changed is now T is 20. So when I set it up, it's going to be exactly the same, except for up here in the T spot, right? I'm going to put a 20. So go ahead and pause the video, set up your account, try to work through and simplify, try to get to a final answer, check back with me, and then we'll write the sentence together at the end. All right, pause the video now. Did you set it up right? Here's what I got. Check to see if you set it up right. If so, pause it again and quickly calculate it. When I come back, I'm going to have the whole problem done out. All right, here's what I got. I did make one little shortcut that I didn't do the last time, so I just want to point it out. After I set it up, when I simplified the inside the parentheses to 1.05, I also simplified my exponent. I did 1 times 20 and just put 20. So I combined those steps into one. So you may have one more step if you did them separately. But you should end up with A equals 265.32977705. When we go to write our final answer, we are working in money. So I'm actually going to cut our number off right here because this is dollars and cents are only 2 decimal places. This 9 here is going to tell me that that 2 has to round up to 33. So when I go to write my final answer, I'm going to say at the end of 20 years, I will have $265.33 in my savings account. So you want to make sure that you use words like savings account, how many years you're looking at, the dollar sign, all that stuff those are all context words and context symbols and things that say that you're taking all this math that we did and you're putting it back into the context of the problem. So when we're doing these word problems, you're starting off with words, you're translating it into math, you're doing the math, and then you're putting it back into the words. And so this is a big place where a lot of people lose their score goes down, or lose points, I guess you could say. But for criterion D, if you're not like writing your final answer as a sentence, that's you're not showing that you can connect your work back to the real life situation. So that's very important, and it's a very easy way to boost your grade a little bit in criterion D. Even if you had the wrong answer, still showing what your answer means is important. So it seems like the more compounding periods in a year, the more money you should make. The question is, does that make a big difference? So that's what we're going to explore on the next page. So if we turn our page to number 3, it says compare the amount of money that you would have after 20 years if it's compounded 2 times each year, which is semi-annually, 4 times per year, which is quarterly, 12 times per year, which is monthly, 365 times per year, which is daily, and then hourly. So how many times a year would hourly be? So we know there's 365 days in a year. We know each of those days has 24 hours. So if we do 24 hours in a day times 365 days, that means there's 8,760 hours in a year. So here would be our n, which is our compounding number of times it's compounded a year, is going to equal 8,760. We did that because we did 24 times 365, and that's how we got that number. So what we're going to have to do is compare the amounts. So that means I'm going to get a bunch of different amounts of money. One where, well, after 20 years. So that means T is going to equal 20 here. But it's going to be compounded different ways. So I'm going to have to calculate the amount of money. That's A. For 20 years, for T equal to 20, when it's compounded 2 times a year, which means when n equals 2, 4 times a year, that's when n equals 4, 12 times a year, that's when n equals 12, 365 times a year when n equals 365, and hourly when n equals 8,760. We got to find a way to organize it, display, and explain what we see. So comparing them means that afterward I'm going to have to talk about what I see. How do they compare and contrast to each other? What are similarities? What are their differences? I'm going to do all the math out, but then I'm going to have to organize it. So one way we could organize it, since there's going to be a bunch of A's and a bunch of different N's that I'm going to use, is I could make myself a table. I could make a table where I keep track of what was the N and what was the amount of money left in the account afterward. We already did one of them. On the front page, we did when the N is 1, we just finished. After 20 years, you'll have 265.32977705. So my next things are going to be to calculate when N is 2, like it says up here, when N is 4, when N is 12, when N is 365, and when N is 8,760. And so luckily we have this formula to use, so I don't have to do each step out one at a time like we were doing on the whiteboards. But I'm going to keep log of all my answers over here. So I'm going to use this space to do all the problems out. I'm going to try to write a little bit smaller so that way we can fit it all. And then maybe down here I can write my thoughts after I look at the table. So I'm going to need to do it for each one. So I'm going to start off with my A when n equals 2. And so I'm looking for A, same principal amount, 100. Then I've got 1 plus the same rate, 0.05, over n, which is 2 this time, so it's going to have a 2 in the denominator here. Close my parentheses, and then I have to do my n, which is 2, times t, which is 20. So I'm going to go through and do this one, and then we're going to do it again for n equals 4, and for n equals 12, and n equals 365, and n equals 8760. So we'll try to go a little quicker now. So a equals 100. I'm going to type all of that in the calculator so I can figure that out. And I'm also going to condense this exponent at the same time. So we'll do the first one first. So I'm going to do 1 plus 0.05 divided by 2. So that whole thing in the parentheses is 1.025. So parentheses 1.025. And I'm going to raise that to the 2 times 20 power, which is 40. So now I need to do I did my parentheses, now I need to do the exponent. I actually need to do 1.025 to the 40th power. 2.685, blah, blah. I'm going to write that down. A equals 100 times 2.685063,838. And now I'm going to do that times 100. So here's a quick trick. Rather than typing all this number in again, I can literally just hit times 100. And you see how it says ANS? That means it's taking your previous answer, which is this, and it's multiplying it by 100. So that's a faster way to get things in the calculator. So when I multiply that by 100, we get 268.5063838. So A is equal to 268.5063838. So I'm going to fill that in my table over here. 268.5063838. And now I'm going to redo the same thing, but when n equals 4. So go through, set it up, calculate for n equals 4. Check back, I'll show you the work. Pause the video. Here's a quick check. Check your answer. And now we're going to do it for n equals 12. All right, pause your video. All right, here we have n equals 12 and our final answer. Pause if you need to catch any of that. But I'm going to ask you to calculate for when n equals 365. I do want to show you a really cool trick. So let me set that one up, and then I'm going to show you something on the calculator. All right, so here is n equals 365. So I set it up with our 365. I multiplied these first to see that they're 7,300. And I did that in that order. And then I put this parentheses in the calculator because look at how long this number is now. 1.000136986. So I wrote it all out, but I don't want to have to type in that 1.00138 blah, blah, blah. And then the next step I have to do is raise it to the 7,300 power. If you have that as your last answer in your calculator and you just hit the power button, this little caret button right here, it will take your previous answer and raise it to a power, and you can just type 7300 without having to type all of that back in. So there's a quick shortcut also, so you don't have to always type in every single digit as well. So go ahead and pause, finish this up, and then go ahead and do your n equals 8,760 and check back. All right, so here are the last two. And so the last step that I have to do, well, two steps. I'm going to fill in the rest of my table over here with the numbers that I got for my answers. And then we're going to look at them and see what we notice. If there's anything that we can see that's happening that is worth mentioning. And you may have noticed as you are calculating them, what I'm hoping you're going to see when you look in the table at the numbers. Okay. So the last part we have to do is look at this table and compare. What happens as our compounding, our number of times the interest is compounded throughout the year, is changing from 1 to 2 to 4 to 12 to 365 to 8,760. What's happening over here with the amount? So take a minute, look at that, write down an idea, and then come back. All right, so hopefully as you're looking down the table, you're noticing that the number of times it's compounding is increasing. And as that happens, this is also increasing. It's going from 265 to 271. Now, is that a lot of increase or not a lot of increase? Not very much. If you actually subtract this number from this number, it's about $6.51. So we could say from compounding it once a year to compounding it every hour throughout the year, it's really only changing about $6. So I'm going to write that idea down here in this little space I have left. You can say the account only gains about $6.51 when it goes from compounding once per year to compounding every hour. So you do get more money the more often they compound, or the more they compound. But not a significant amount. And that's something to note. It's not significant, meaning it's not a lot. Of course, I'd always want more money. $6 is a little bit more money. But if I had to choose between the account, I would choose the one that gives me the more money. The more money you put in, the bigger that difference is going to be, probably. But based on the fact that we only put in $100, we're only seeing about a $6 difference. So looking at our work up here in this table, we want to describe a pattern. What is the pattern we see in the way the number of compounding periods is changing and the amount of money is changing? So hopefully you notice that it's not like adding the same number every time. It's doubling at the beginning, so times 2, but then it's times 3, and then it's a lot bigger. It's like times 30, something like that. And then times 24 for this last one. So it's not even growing at a constant rate. It's not adding a constant number. It's not multiplying by a constant number. So there's no common difference or common multiplier. Those are the words that you probably used last year. But we do notice that the n is increasing pretty rapidly. And while that's happening, our a is increasing pretty slowly. So we could say that. We could say as n increases fairly quickly, although not by a common difference or common multiplier, common ratio is what they call it, or ratio, the a is growing fairly slowly. And that's what happens when we're looking at this kind of exponential equation. We have an exponent in our equation in our formula, so it's an exponential growth. So now it says looking at graph number 3C on Desmos. So the link to this graph is in the agenda. I want you to look at the graph and then write down what you notice. How does that connect to the pattern that we just saw? So go ahead and pull that up, take a look at it, jot down some ideas, and then come on back. So as you look at this graph, the graph is of the function we just graphed, with 100 as our principal amount, 5% as our interest, 20 as our years, but we kept the n, because that's what we kept changing, as our x. So both down here and up here we have an x. And so we look at this graph, and it starts right here where the red starts at 100, because that's our amount that we start at. That's our initial amount of investment. And then if you notice, it goes up pretty quickly and then kind of curves off, and now it's kind of like going sideways. But if we look, it's starting to curve off here at around 262, and then as I go over here, it's about 268, and we keep looking at that y value, it's 270, and I go all the way over here, and it's about 271, and so it's slightly increasing, even though it looks flat. And if I zoom out a little bit, we can see it keeps going over here. 271, 0.22, 0.34, 0.37, 0.45, 0.48. So it's still increasing, but only really the cents are increasing at this point. It's such a slow increase as we go over there. So what did we see as we were looking at this information? We saw a quick increase like we originally saw looking at the graph, and also looking at our table, we saw the same thing. And then we saw this quick increase that we saw here. It went like straight up, and then it started to flatten off. And as we look here, that same kind of thing is happening. It's starting to flatten off. It's increasing still, but increasing very slowly as we go along. And it's kind of flat where it's almost, at 271, at 271 again, at 271 again, and only the cents are really what's changing. And so how can we say that here, that what we saw? So we notice that the graph shows that as the n increases, the amount also increases, right? Because we saw it going up and over at the same time, so that we know that they're both increasing. So the graph shows that as n increases, the amount also increases. But n increases quickly, and the amount, that's our A, remember, sort of levels off around 271. Maybe say just above 271. Matches what we saw in the table, because the same thing happened there. This matches what we saw in the table, because our amount also started to slow down around 271. And so actually, our graph was approaching that number, whatever is just above the 271. And our numbers here were also approaching. They started at 265, then 268, then 270, then 271, 271, 271, where only the change or the cents were changing. So it turns out that the value we actually found in our compounding problem is 100 times a very famous irrational number named e. So here is a new number for you to think about. Because e is irrational, it means it is a non-terminal, which means it doesn't end, non-repeating, there's no pattern in the decimals, a decimal number, much like the number pi. You've seen pi before, 3.141579, blah, 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 blah. No patterns, doesn't repeat, never ends, always a remainder, so you just keep going. The very first few digits of E are 2.7182818828552355360287471357. Those are the first few digits. So it just keeps going forever. And that number, 2.71828818, is very similar to this number that we got here, 2.7, well, 100 times it, 271.838. So we got 838 and it was 828. So we got very, very close to this number. It's almost as if the graph was going towards this number and never quite getting there. And so like pi, E is a number that occurs in mathematics in many real-world problems or situations, including exponential growth. So E is a number we use when we're looking at exponential growth. One of the formulas using E results from the thinking that we just did about the compound interest. It can be shown that the amount of money, A, in a savings account where money is compounded continuously, so faster or even more often than hourly, continuously, forever, like every second it's done compounding the interest, it's going to do it again and again and again. So whenever you see this word continuously, that means we're going to use this formula instead. So we've got two formulas to look at, and they look very similar. This one's a lot shorter, though. They use a lot of the same information. This one still uses P for the principal. E is actually a number, so that's weird because we're used to that being a variable. So we're not ever going to fill anything in for that E. We're going to use actually E in the calculator, and I'll show you where that is. R is still our annual interest rate, but you'll notice now it's only in the exponent, and T is still the number of years. A is still our amount. So what's not included here is the N factor. So when it is continuously compounded, we don't have a number to put in for N. We use this formula instead. So what we're going to do next is compare. How does this formula compare to the one we were already using? So it says it's very typical for savings accounts to be compounded monthly. Compare the amount of money in two savings accounts after 10 years. I'm going to quickly put that in a circle, or a box, I mean. So T is equal to 10. With the same initial investment of $500, okay, so initial investment, $500. This is going to be our P. And an interest rate of 3%. So that means our R is going to equal 0.03 in each account if the first account is compounded monthly and the second account is compounded continuously. So compounded monthly means N is going to equal to 12. If I'm looking at it compounded continuously, I'm going to use the E. So I'm going to have to do two calculations. One where N is equal to 12, where it's monthly. And I'm going to have to use the formula from the front of our paper, which is this one. A equals P parentheses 1 plus R over N to the N times T power. And then I'm also going to have to do it continuously, where I'm going to use this new one. A equals P E to the RT power. Or PERT, if you want to call it that. So I'm going to have to compare them, because if I go back and read this again, it says it's fairly typical for savings accounts to be compounded monthly. That's this one. Compare the amount. So I missed this part before. So I got to come back and compare these two afterward. Compare the amount of money in the two savings accounts after 10 years. With the same initial investment, so same number of years, same initial investment, same rate of 3%. Just what's different is this one is monthly and this one is continuous. So we're going to calculate them both and we're going to compare them and see what we see. So go ahead and set this one up and do your calculation. Pause your video, come back, and then I will show you what I got. And then I will show you how to do this one. So pause your video now, check back once you have an answer for monthly. All right, let's see if I can adjust this a little bit because I got a glare. All right, so for the monthly savings account, you should have got that the amount would be in after 10 years would be $674.6767736. So if we're counting that as dollars, it'll be $674.68. All right, so now we got to do this continuous one. So we need the same information. We start with A. We don't know that. We're going to keep A here. Principal is 500. E is a number. I'm just going to put E for now. I'll show you how to use the calculator with that. My exponent is going to be R, which is 0.03, times T, which is 10. So what we're going to do first, since there's no parentheses, is we're going to work on combining these numbers or multiplying these numbers to get our exponent. So we're going to get A equals 500. E, if I do 0.03 times 10, I get 0.3 to the 0.3 power. So let me show you in the calculator. 0.03 times 10, so 0.3 power. So what I need to look for is over here on the side, down here you see this little blue thing that says e to the x. So I'm going to press the second button, and then I'm going to press that button. And I'm going to get e to the something power, and I'm going to be able to type in 0.3. I'm going to hit enter, and I'm going to get 1.34. Let me write this down. So we get A equals 500. I'm going to now put a parentheses in because this has to be multiplied, times 1.3498588808. Close my parentheses. Now all I have to do is multiply that number times 500. Since I already have it as my last answer, I'm going to do times 500. I'm just going to take my last answer and do times 500, hit enter, and the amount will be 674.929438. So now we've got both numbers. So continuously, we've got about $674.93. And for this one, monthly, it's $674.68. So how do those two things compare? Because that part of it says to compare. So we noticed with compounding interest, it's obviously more money, but you get about like 25 cents more on your investment. So it's more, but it's not much more. So let's write that down here. We can say with compounding continuously, you get about 25 cents more on your investment. It's more, but not much more. So there's another graph for us to look at on Desmos, graph number 5, and I want you to try to make a conclusion about what the effect of changing the number of compounding periods has on our savings account. So what's a general statement you can say about compounding a certain number of times and how that's changing and what that's doing overall? So kind of a general rule if you think of it that way. Pull up that graph, take a look, jot down some ideas, and then I will try to review it with you on here as well. One thing to think about is try to use the zoom feature to go in or out, or you can click and drag the graph around to try to see if you can notice anything. So taking a look at graph number 5, if you look here, we have two things graphed. The blue graph is our compounding continuously graph, 500e to the 0.03x. And so it's over time. That's why the time part is our x. And then the red graph is the compounded monthly graph. So I'm going to close this just for a second. Actually, let me show you. If I turn off the blue graph, there's the red graph. If I put the blue graph back on, they kind of look like there's only one. And so we notice that it's starting low and going high. And if I zoom out, I still only see the blue graph. But I'm going to zoom in closer so that you can see there actually are two lines here. But our red graph, which is our monthly, so if I look at 116 years is here. That's the red graph is down here, sorry. So about 116 years is about $16,000, $165. But our blue graph at 116 years is about 16,231. So they're still very close. I can even go down closer to where we were. Sorry, gotta drag it. And if you see, they're kind of not parallel, but they almost look parallel, but they're curved, so we know that they're not exactly parallel. And the red one's always below. So our monthly interest is always going to be below the continuous compounded interest. So we're going to get more in our account if we use the continuous, the PER to the RT. There we go. See, it's starting to level out or go a little more horizontal now. But if you see, now they're getting closer together. So they start off really close together, and that's why we couldn't even see that they were two separate graphs. And then as time goes on, so we're at about 42 years into the investment process, and they're starting to slightly be different, more noticeably different. And then as we go on, they get more and more apart. So as time goes on, the blue one, which is our continuous one, will eventually be a lot more, but for now, it's really just only a little bit more. So if we go back to our paper, what can we say here? The beginning of the graph, the investment looks to be about the same, but that continuous one is ever so slightly more money. Eventually we can see it. They get farther and farther apart, but they're still really, really close. So looking at the graph, we can see that the investment is the same, but eventually the graph that is compounded continuously is slightly more money than compounded monthly. So what overall statement can we say? We can say it's obviously better to have your interest compounded more often. But the difference isn't that significant. With only a $500 investment. Not more than a few dollars. Right? If you were to invest like $5 million or $5,000 or $500,000, that might make more of a difference. But we didn't see a ton of difference. Here it was only a few cents. So that's the difference between those things. Obviously, it's better to choose continuous, but you can also get a good deal, almost the same deal, choosing it monthly. So we're going to take one last look at a little bit more with the letter E. We're going to take a look at the function with E on the back page here. So it says, since E is widely used to model exponential growth and decay in many contexts, I know you've talked about those things before, especially in biology, let's get a little more familiar with base E exponential function. So here's the function, f of x equals e to the x power. Make a prediction about the graph of f of x. Explain what prior knowledge you used to make your prediction. So what do you think, knowing that this is an exponential graph, what do you think it's going to look like? So jot down some ideas maybe about the shape of the graph, maybe about whether you think it's going to be a slow or a quick increase or a decrease. Pause the video, write some ideas down, and then we're going to look at making the actual graph. If you need a little help writing a prediction, I structured one here. Go ahead and pause the video, jot that down, and fill in the blanks with your thoughts. All right, to create our table and our graph and describe the mathematical features of f of x, and then we're going to check our graph with graph number 7 on Desmos. So we're going to use this graph to create our graph. We got to make a table. That would be the best place to start. So let's make a table over here. We're going to do y equals e to the x power. So we're going to pick different exponents for e. So we know when picking exponents, we should be picking negative exponents. So I'm going to do -2, -1, 0, 1, 2. If we can fit all of those on the graph, actually I can't fit -2, so I'm going to do one more. 3. See if we can fit all those. And then in our calculator, we're going to do e to the -2 power, e to the -1 power. So do that, pause the video, do that, and then jot them down. So remember the E button. You're going to go down here, you're going to hit second, then you're going to press this one that looks like an LN. It has a little e to the x, and then you're going to type in -2, write down your answer. I would say let's go to about 4 decimal points. So for this one, we can put 0.1353, because after that 3 is another 3. So now do -1, 0, 1, 2, and 3. All right, you should have your table filled out. If not, pause the video and finish that before checking your answers. Now, here's what I got. So now we're going to take this and we're going to graph it. So we've got, this is -1 here. So I'm not going to be able to fit -2, but -1, our numbers are mostly below 10. So I think I can count 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I'll be able to fit everything but the last one. The first one and the last one won't fit. So we'll get 4. We'll get these 4 in the middle on our graph. Okay. So -1 is about 0.36, so that's less than half. So I'm going to go about a little less than half, about a third of the way, and make a dot. Then I've got 0, 1, so I'm going to go 0, 1 up here. I've got 1 and 2.7, so I've got 1 and about almost a 3. And then I've got 2 and 7.3, so 2, 3, 4, 5, 6, 7, 7.3, so about here. So does that look how you thought it was going to look? What kind of graph is this? I bet you were thinking it is a J-curve. I believe that's what you call it. So we can say it is a J-curve. You've used that word in science before. Because we got to describe its features, right? That's what it says up here. Describe the mathematical features. So that means it's always increasing. Slow increase, and then it starts to rapidly increase. So we can say that too. Slow at first. and then click. And then we can talk about the domain and range, because there's no minimums or maximums really to talk about. But our domain, since it is going this way forever, it's going to be negative infinity. And it is still going to the right, but slower this way, but it's going up and to the right as I keep going. So it's going in both directions. So our domain will be negative infinity to infinity. And when we look at our range, hopefully you noticed that it's coming down and then kind of flattening off like we talked about. So it's not actually going to go below this x-axis. It's going to kind of get lower and lower and lower and lower and approach the x-axis, but never actually get there. So it's never going to get to 0, which is why we put 0 with the little parenthesis and not the square bracket. So the range is going to go from 0 to infinity because it's approaching the 0, the x-axis, and it's going to go all the way up and keep going. All right, so now we've looked at both types of formulas for our investments as they accrue interest, either compounded sometime throughout the year or continuously. And then we've explored our letter E, which is an exponential function that is used when compounding continuously. So the next step is going to be to take some notes. So grab this paper from the front of the room. You're going to give yourself 2 examples, one using this formula, one using this formula, and then down here you can define what each of the letters are. I will give you the definition for E right now, and then you can fill in any other notes you want to write to your future forgetful self. So you may want to consider thinking about some of the things that we worked through this packet that you might want to add in there that are not either covered in these 2 examples or in this side over here where the vocabulary is. So you may want to write some things about maybe writing your sentence, your final answer in a complete sentence over here, or anything you need to remember when looking at these formulas, like what order to do things in or things like that. So go ahead and take your notes, glue this into your notebook, and then I will give you the CYU to work on next time I see you.